Hello everyone, my name is Danish and you're watching Code Notes. In the previous tutorial, we learned a few things about thread memory stack in Visual Studio. But now we will learn how to manipulate the stack in assembly. Before we do that, there's something interesting we need to know about conditional jumps in assembly. When we wish to check if the value of a CPU register is 0, then we use the compare instruction like this. If the value of the CPU register EX is 0, the compare instruction will set the 0 flag to 1 within the CPU. This jump instruction, JZ, which stands for jump if 0, it will check for the 0 flag within the CPU. If the flag is set, the jump is taken. So in this case, the jump is taken because we are assuming the value of EX register to be 0. When the compiler is generating some machine code from C++, let's say if we have some C++ code that looks like this, then the compiler will use the test instruction. For example, if the value of EX register is 0, then the test instruction will set the 0 flag to 1 within the CPU, and the jump will be taken. This code is equivalent to our previous code. It is completely optional whether if you wish to use the compare instruction or the test instruction. It is a good practice to use the compare instruction all the time instead of the test instruction. But when we wish to check if the value of a CPU register is 0 or not, like we are doing right now, then in this case it is better to use the test instruction instead of the compare instruction. There is barely any performance difference between these two instructions. In assembly, the push instruction is used to push 4 bytes of data on top of the memory stack within RAM. And the pop instruction is used to pop 4 bytes of data from top of the memory stack within RAM, and these 4 bytes are stored within a CPU register. When we have some data in a CPU register like EX, which we want to keep for later use, but we also want to do some other operations using the CPU register, then we use the push instruction to store its data on the stack. Create a new project. I will name it push and pop. We will write inline assembly for this example. I will show you how to write a loop in assembly where the code will iterate 10 times. Let's run the program and attach our debugger. Imagine if we have some important data in the EX register. Let's say if we have the number 50 in EX and we don't want to lose it, then we use the push instruction to push the 4 bytes of data on the stack. Now we can use the EX register for other operations if we want to. And once when we are done, we can pop the 4 bytes of data from the stack. And since we wrote EX here, the data will be stored in EX register. We need to use a CPU register for the loop index. We will use EX and let's initialize it to 0. Then we define a label so we can jump back here using the jump instruction to repeat the code. Now we can write code here if we want to, but I will keep this empty. The increment instruction will increment the value of the register by 1. We use the compare instruction to check if the value of the EX register is lower than 10 or not. If the index is lower than 10, the control will jump to repeat code label and repeat the code again. This code will be executed 10 times. Once the value of EX becomes 10, then the control will go to the next instruction. The pop instruction will pop 4 bytes of data from top of the stack and store the value in EX. The old value of EX register, which is 50, has been restored. There are two CPU registers which are used to manipulate the memory stack of a thread, ESP and EBP. Both of these registers are 4 bytes in size, just like the general purpose registers, except the purpose of these two registers is to manipulate the memory stack of a thread. The ESP register is called the stack pointer. The ESP register will always point to top of the stack by holding its memory address. Whenever the push instruction is executed, it will allocate 4 bytes of space on top of the stack by subtracting 4 from the value of ESP, and the value of the register will be copied to the allocated space. The pop instruction will do the opposite. It will first copy the 4 bytes of data from top of the stack to register, and it will deallocate the 4 bytes by simply adding 4 to the value of ESP. Whether we push or pop data on top of the stack, the ESP register will always point to it. On the other hand, the EBP register is called the base pointer. To understand how the EBP register is used in assembly, let's look at this example. We have some C++ code for calculating the average of 3 numbers. We will write the code in assembly. In just a moment, all of it will make sense. Let's compile the program and attach our debugger. We first push the 3 parameters on the stack for getAverage function. Depending on the calling convention, function parameters are pushed in right to left order, and then we use the call instruction to call the function. The call instruction will first push the 4-byte address of the next instruction that comes after the call instruction and then call the function. The reason why it pushed the address of this instruction on the stack is because when the program is done executing this function, then the program will return the control back, and the address on the stack is used for jumping back there. These few lines of code on top of the function is called the prologue. This is where we create the space for local variables, and if you look at the bottom of the function, these few lines of code is called the epilogue. Here we deallocate the space we created for the local variables and return. So we first push the value of EBP register on the stack, and then we move the value of ESP into EBP. Now ESP and EBP contain the same address, which means both of them are pointing to top of the stack. We can right click here and change the value representation to decimal or hexadecimal if you want. Nonetheless, both of these registers will have the same value. Here's the interesting part. We created a space for 2 local variables by subtracting 8 from the address within ESP. The size of each local variable will be 4 bytes because the data type is int. If you look at the stack, the value of ESP got updated. So ESP is still pointing to the top of the stack as always. But if you look at EBP, EBP still contains the old address. This means that EBP is still pointing to the old location on the stack. This is exactly what we need. Now we can use the EBP register to access and modify the data on the stack. We need to calculate the sum of the 3 function parameters A, B, and C. If you look at our stack, this is how we can use the EBP register to access and modify the data on the stack. For function parameters, we simply use the positive sign to access them because they come before the location the EBP register is pointing to. And for data that comes after the location the EBP register is pointing to, we have to use the negative sign for them. The square brackets instructs the compiler that we are dealing with a memory address. The move instruction will move the value of the function parameter A from memory into the ECX register. Now ECX contains the value 10. Then the add instruction will add the value of two operands together and store the result in the left operand. We are adding the value of function parameter b with the value in ECX. ECX will now contain the value 15 because we added the value 5 to it from the function parameter b. And then we add the value of the function parameter c to the value in ECX. Now ECX will contain the value 30. And here the value from ECX will be moved into the sum local variable, which is on the stack. This code will perform the division for calculating the average. As we can see, we are using the divide instruction. This instruction is called bitwise exclusive OR. It will set the value in EDX to 0 if you write the name of the same register for both operands. We are doing this because the divide instruction will store the remainder in EDX. The dividend must be moved to EX before calling the divide instruction. So we move our sum into EX register from the stack, and we can move the divisor to a register of our choice. Let's move it to the ECX register. Finally, we have the divide instruction and name of the register which contains the divisor. When the divide instruction executes, the quotient is stored in EX register and the remainder is stored in EDX. If we look at the registers, EX now contains the average, which is 10. Then the average is moved from EX into the average local variable on the stack. The return value is normally stored in EAX, so we'll move the average into the EAX register. This instruction will deallocate the space for local variables on the stack by simply adding the number 8 to the value of ESP. So basically, the sub instruction is used to allocate the space on the stack and the add instruction is used to deallocate space. We can also use the pop instruction instead of the add instruction. But the add instruction is faster because the pop instruction can only clear 4 bytes at a time. This instruction is not actually needed here. We can remove it and the code will work fine because in the next instruction we are restoring the old value of ESP, which will clear the stack for us. At the end, we have to restore the old value of ESP before exiting the function. And we do that by moving the value from EBP to ESP. The value of EBP, which we pushed on the stack first, we must restore that as well. And the pop instruction will pop the 4 bytes of data from top of the stack and store them in EBP. The return instruction will clear the 4-byte address from top of the stack and jump to it. We use the add instruction again to clear the function parameters on the stack. So EAX still contains the average of the 3 numbers, which is 10. We can write more code to print it here if we want. Whenever we define a function in C++, the compiler will automatically use a calling convention for it. A calling convention is basically a set of rules that define how function parameters are passed to the calling function, how these parameters are cleared from the stack, and how the function result is returned. In Visual Studio, there are 4 main calling conventions for C++. CDECL calling convention. The caller function must push and clear the function parameters on the stack. The return value is stored in EEX register. The Visual Studio compiler will automatically use this calling convention for all globally defined functions and static functions of classes. For example, we have some code here for calculating the sum of 2 numbers. Since sum is a global function, its calling convention by default is CDECL. We can also write it like this. This will force the compiler to set the calling convention to CDECL for the sum function. If we put the sum function in a class and make it static like this, the calling convention of the static function will be CDECL, just like this global function. Let's see how we can call the sum function in assembly. We first push the two function parameters a and b on the stack in right to left order, and then we call the function. When the function returns, the two parameters are cleared from the stack using the add instruction. And finally, the return value is stored in EX register. We then move the return value into the C++ variable and print it. std call calling convention. This calling convention is mainly used by the Win32 API functions on Windows, like the open process function of the Win32 API. The caller function must push the function parameters on the stack and the calling function must clear them. The return value is stored in EX. For example, the calling convention of this function is cdecl by default. But if we want to change the calling convention to stdcall, then we have to write it like this. To call this sum function in assembly, we simply write, we first have to push the parameters in right to left order and then call the function. Before the sum function returns, it will clear the function parameters on the stack. So we don't have to clear them here, and then we move the result into the sum variable and print it. Fast call calling convention. This calling convention is hardly used by the compiler unless we specify it. The name is also misleading because the fast call calling convention is not faster than any others. Unlike the cdecl or stdcall calling convention, for the fast call calling convention, the first two parameters are passed in ECX and EDX registers, and the remaining parameters are pushed on the stack. The calling function must clear the parameters before returning, and the result is stored in EX register. For example, just like the stdcall calling convention, fast call is not used by default. We have to specify it if we want to use it. This sum function takes three parameters. When calling the sum function, the first parameter a must be stored in ECX. The second parameter b must be stored in EDX, and the remaining parameters must be pushed on the stack. And then call the function. And before returning, the sum function will clear the parameters, so we don't have to do it here. Then we move the result to the sum variable and print it. This calling convention. This is the default calling convention of C++ class methods in Visual Studio. The first parameter is passed in the ECX register, and the remaining parameters should be pushed on the stack. The calling function is responsible for clearing the parameters. The return value is stored in EX. For example, if we define a C++ class with two methods, the calling convention is set to this call for these two methods by default. We can also write it like this if you want. It is optional. The first method is the constructor. The second method will update the two members of the class. Since these two functions are methods of a class, both of these functions have a hidden parameter, which is literally called this. For example, we can access the score A and score B members of the class using this parameter. The this parameter is passed in the ECX register instead of the stack. We can call the setNewScore method in assembly like this. Let's compile and run the program. Now let's attach our debugger. We first create an instance of the class and store it in myScore variable. Then we store the address of the instance in our pointer variable. If we look at the variable data, we can see that it is simply an address of myScore instance. And then we store the address of our setNewScore function in score function variable. We can see that the score function variable contains the address of setNewScore function. And by the way, it is important to write a typedef for the setNewScore function since we want to store the address of setNewScore function in a variable. This is the class name. These are the two parameters. We can choose any name for the typedef. For this calling convention, the first parameter is the address of the class instance, and we must place the address in the ECX register. Then we push the two parameters on the stack and call the function. The stack is cleared by the callee function, so we don't have to clear it here. The result is stored in EX and then we print it. The EIP register, also known as Extended Instruction Pointer, is a 32-bit register which keeps track of the next instruction to execute. As we know that every single memory address within RAM can hold up to 1 byte of data. The EIP register will contain the address of the first byte of the next instruction to execute. Let's look at this example. Start cheat engine. For this example, we will use GT San Andreas. Let's add a breakpoint here to halt the program. We can look at the register values on the right. Press Ctrl G. We will see the address of the highlighted instruction. The EIP register will always contain the address of the first byte of the next instruction to execute. If we copy this address, click on the hexadecimal view at the bottom, press Ctrl G and go to the address. We can see that this is the first byte of the next instruction the program will execute. Here the first byte is A1. Let's execute the highlighted instruction by pressing F8. We can see that the value of EIP register got updated because we executed an instruction. Now EIP contains the value of the new highlighted instruction. If we press F8 again, the value within EIP will be updated again. If I click on a random instruction, press Ctrl G and copy its address to EIP, pressing F8 one more time will make the control go to this instruction and execute it. The program will probably crash if we continue the execution because we skipped some instructions. However, we can see that the control will always jump to the address stored within EIP when executing instructions. There are two more registers within the CPU that work just like the general purpose registers. ESI and EDI. SI stands for Source Index. DI stands for Destination Index. Both of these registers are 32-bit in size. These registers have fancy names, but they can be used for any general purpose. Here's a complete list of general purpose registers. And these two are the stack registers. ESP and EBP are only used to manipulate the stack. When we are accessing data on the stack using the move instruction, the register EBP contains an address. We add an offset to the address within EBP or subtract an offset from it to get the desired data on the stack. But what if we want to move the calculated address of the data on the stack instead of the data itself? Well, that is when we use the LEA instruction. LEA stands for Load Effective Address. If we have some code like this, let's assume that the value of EBP is some random address. And if we add the offset 4 to it to access a function parameter, then the calculated address will be moved into EX. Let's look at an example. We have a function that takes two parameters. Both of these parameters are pointers. The size of a pointer variable is 4 bytes for 32-bit programs. In this example, we will call the function and set the value of the addresses within the pointer variables. Assembly code is just like defining a new function in C++ with some code in it. We first store the value of EBP on the stack, and as we know that ESP points to the top of the stack, we move the address within ESP to EBP so we can manipulate the data on the stack. And then we create the space for the local variables on the stack. This LEA instruction will move the address of the second local variable into EX, and then we push the address on the stack using the push instruction. We do the same for the first local variable. When the function is called, the parameter 1 points to the first local variable on the stack that we created before calling this function, and the parameter 2 points to the second local variable. If we check the function data, we can see that these two parameters point to a location in memory by holding a memory address. Then we update the value of the memory addresses and exit the function. We have to clear the function parameters on the stack because the calling convention of that function is cdecl. I added these two instructions just for illustration so we can see the value of the two local variables in Visual Studio. We move the value of the first local variable into EX. We can see that the value of EX is 5. Then we move the value of the second local variable into EX. Now EX contains the value 17 in hexadecimal. We can change this to decimal view and we will see the value 23. And as usual, we have to clear the local variables on the stack. Restore the old value of ESP and EBP. Now it's time to decompile some code with IDA Pro. We can go back to the example of this calling convention. Let's compile the code in release mode. And then open it in IDA Pro. This is our main function. Press F5 to decompile the code from ASM to C++. When we compile the code in release mode, the compiler will do optimizations and make the code faster. These two lines of code come from the constructor of myScore class, but since the code has been optimized, the compiler generated a line code of the constructor function. So these two lines come from the constructor. If we take a look at the setNewScore function, we can see three parameters. The first parameter is the address of myScore instance. The calling convention of this function is this call, which is why the first parameter is passed in the ECX register, and the remaining parameters are passed on the stack. Go to the IDE view. This code actually comes from here. Here's a side-by-side view. IDE Pro will show the numbers in hexadecimal. The H at the end shows that this is a hexadecimal number. The score function local variable contains the address of setNewScore function. Let's go to the setNewScore function. First, the EBP register is pushed on the stack. Then the address of ESP is moved into EBP. We can see that the EBP register is used to access the function parameters on the stack. The ESI and EDI registers are also used in this function. But here's the interesting part. Before any data is moved into the ESI or EDI registers, their value is first pushed on the stack and then they are used. The value of the parameter B is moved into the ESI register, and the value of parameter A is moved into the EDI register. At this point, the ESI register contains the value of parameter B, and the EDI register contains the value of parameter A. Then the address of the string for calling the printf function is pushed on the stack. IDE Pro is showing the ECX register as this for making it easy to understand. But if we open the executable with a different disassembler, then it will show ECX instead of this, so don't get confused here. Here, the ECX register contains the address of my score class instance. Click here and press F5. We can see that the ECX register is used to access the class members for the instance. Since the score A member comes first, we have to use the offset 0 when accessing it. The offset of score B member is 4 because the type of score A member is integer and the size of integer is 4 bytes. If we hover our mouse cursor over these members, we can see the offset. If we go to the ASM code, we will see the same thing. The EDI register contains the value of parameter A, and the ESI register contains the value of parameter B. The offset 0 is added to ECX for score A member, and the value of EDI is moved to it. And then the offset 4 is added to ECX for score B member, and the value of ESI is moved to it. The address of the string is still on the stack. Then the print function is called and the string gets printed. Now it's time to clear the stack in reverse order. We can use the pop instruction if we want to clear the 4 bytes and store the data in a register. We can use the add instruction to clear more than 4 bytes. And unlike the pop instruction, the add instruction does not store the data in a register. It just clears them. So we clear the 4 bytes of the string address on the stack. I will explain this instruction in a moment. If we are going to use the pop instruction to clear the 4 bytes of data on top of the stack one by one, then we must do it in the reverse order. We have to pop the EDI register first, and then ESI, and then EBP. We can see that the pop instruction is used in the reverse order if we compare it with the push instruction. The final instruction is the return instruction. We know how this instruction looks like in C++. Since the calling convention of this function is this call, the calling function must clear the parameters from the stack. The number 8 is the total size of the two parameters on the stack. We have two function parameters here, A and B. Before the controller jumps back to the caller function, these two function parameters A and B are cleared by the return function. If we click on this LEA instruction and press F5 to decompile it, we can see that it calculates the sum of A and B and moves the result into EX for the return value. The EDI register contains the value of parameter A and ESI register contains the value of parameter B. In Visual Studio, we choose the value 10 for parameter A and value 15 for parameter B. So here, the values 10 and 15 are added together, and the sum 25 is moved into the EX register. The compiler could have used the add instruction to achieve the same result, but since we compiled the code in release mode, the compiler tried to make the code faster. So it used only one instruction to calculate the sum and move it into EX. Now EX contains the sum, which is 25. We can use the escape key to go outside this function. It will take us to our main function. We can see that the result is moved from EX register into the sum variable and printed using the printf function.